Hi everyone, welcome to my Physics 2211 Lab 1, where I try to observe the motion of a hamster ball that's moving at the same speed without changing direction, so constant velocity. I use the app tracker to extract information about the ball's position and time throughout its motion, and then I compared this data to an expected computational model of what the same ball in constant velocity should look like. I applied Newton's second law and the momentum principle to analyze the similarities and differences between these two scenarios, and I found that the ball initially began to decelerate and then accelerated in the positive x direction, so the velocity fluctuated relative to the average velocity. The velocity was not completely constant because I was not able to maintain a net force of absolute zero on the ball, due to factors such as varying friction between the ball and the floor and the movement of the hamster within the ball. So Newton's second law of motion tells us that acceleration of an object is directly proportional to the net force on the object, and it's inversely proportional to the object's mass. And we have that the final velocity equals the initial velocity plus F net over mass, which is acceleration, times the change in time. And so to maintain a constant velocity, we want our final velocity to equal our initial velocity, therefore an F net of 0. And then the momentum principle tells us that net force is directly proportional to the change in momentum, and therefore velocity, since momentum is the product of velocity and mass. And to maintain constant velocity and therefore constant momentum, the net force must be 0. So here's my hamster, Kirby Pichu Ganondorfus III, and so we put her in her ball and gave her a push. Now you'll see I let go of the ball around this 4-inch, 10-centimeter marking, and that's where I began the tracker frame, and continued it until the ball went past this 30-inch or 72-centimeter marking. So this took about 1.2 seconds total, giving us a displacement of 0.62 meters over the 1.2 seconds, so we derive an average velocity of 0.52 meters per second. So here you can see the video. I let go at about 4 and she rolls through. So here we have our tracker where I aim to get the position data, and you can see all the different points as Kirby rolls through in her hamster ball. And so that helped us calculate both position in the x direction and velocity in the x direction, and we were able to derive this graph which shows the velocity is a little erratic, but it's generally upward trending, and the position is somewhat linear. It's moderate, strong linear correlation. So now we go back and we make a computational model of what Kirby's motion should look like for a position and velocity. So to do this, we used our average velocity that we calculated from displacement over time, and we created this computational model here where we derived these two graphs and we have position and time data using this code. So basically we created the ball with the radius in centimeters of the hamster ball, and then we just set the initial velocity, or the constant velocity, equal to the average velocity we calculated based on the timestamp, and we had this while loop run for 1.2 seconds because that's how long the actual video was, and then we had the position changing by the rate of the average velocity. So we see here that the relationship between position and time is perfectly linear, and the velocity is relatively constant. Now with our observed values, we found that the position time graph was moderately strong linear, but it was not completely linear like our expected graph, and then our velocity graph was not constant either, but it was pretty much centered around 0.6 meters per second, which is pretty close to our average velocity of 0.52 meters per second. So now if we compare our observed and expected position side by side, we see that the expected is completely linear, and at first the observed drops down below and has a lower slope, therefore velocity, than the expected, and then Kirby begins to start running in her ball, we think around 1 second, and surpasses the expected position. So our analysis of this situation is that the observed and expected displacement are nearly equal, and the position graphs are pretty close, with the observed fluctuating down and then up, and the hamster ball maintained actually approximately constant velocity, but the variations in velocity were likely due to changes in friction between the ball and the floor, and our hamster Kirby running inside the ball, which actually accelerated the ball in the positive x direction. So our conclusion is that the hamster ball maintained approximately constant velocity throughout its motion, but there's still some noticeable discrepancies between the expected and observed position time graphs, and then we see Newton's first and second laws are applied in this situation because an object in motion stays in motion unless an outside force is applied to it, and here that outside force was friction and Kirby moving in the ball. And we see the initial and final velocities were altered due to the varying acceleration. And so the net force was not maintained exactly at 0 due to varying levels of friction force between the ball and the floor, and also curbing the ball. So just some hypothetical situations. If the axes had been flipped, then the hamster ball would be moving in the negative direction and have negative displacement, negative average velocity, but still the same travel time and same average speed, therefore same fluctuation in the position time graph. And then constant velocity implies zero net force, aka zero change of momentum, but that's difficult to maintain because there's no force to oppose friction after the initial force pushing the ball. Now, if we'd kept this throughout, we would be able to do that. And Kirby says thank you.